Okay, so we start our morning session with Professor Denis Auroux speaking about the geometry of mirror symmetry for non-Fano long Calabi-Yau pairs. Please, Denis.
Okay, thank you very much. Pleasure as usual to be here in Miami, and it's also a pleasure to be here for the second 60th birthday conference of Maxime's. Maxime's not here. I told him not to come because it's too similar to the one he gave at his other 60th birthday conference. So I convinced him that it would be good this time. I didn't tell you guys because I didn't want some people to be in the room. Okay. Yeah, you know, being the birthday person enters some privileges. All right. So yeah, so okay. I'm basically going to tell you, like, say that features of mirror symmetry for things that look like they should work like a Fano situation for mirror symmetry, and you expect to have a mirror-Fano-Ginsburg model, and I will explain how these things are built geometrically. And then when you push at the edges, then you find some slightly surprising things. So the theme is what happens when you see exceptional rational curves in your variety. How does that affect the geometry of mirror symmetry? And so, okay, so the slides are a bit dense, but they are not that numerous, or maybe they are numerous, but not anyway. So the framework I want to use is the Schrödinger-Yau-Zaslow approach to mirror symmetry, suitably reinterpreted over the years. But so the basic question we want to ask is, how do we build a candidate mirror space to a given space? And so I will assume that we start, so here there's a pointer, but it's invisible. Yeah, the invisible pointer is, if you anyway. So we start from a k-learning code, and because mirror symmetry naturally wants to privilege Calabi-Yaus, we make it into a log Calabi-Yau pair by taking a divisor, a union of hypersurfaces that represents the anticanonical class, the first term. So first thing we will do is delete this divisor D to produce an open Calabi-Yau, X minus D, and try to equip it with a Lagrangian torus fibration with, for symplectic people, vanishing Maslov class. For people who have lofty control geometric ambitions, who might find special Lagrangian, that's very hard to do like this. So anyway, we want a family of Lagrangian tori that fills in the complement of D and behaves in a prescribed way near D, namely each n-dimensional Lagrangian torus collapses onto an n-1 dimensional torus field. And out of that, we can build a first candidate space, which I will call the uncorrected mirror of X minus D. And that's a space of pairs consisting of basically a fiber of the projection type and a unitary rank 1 local system on it. So this is producing out of each torus in my Lagrangian family a dual torus of the same dimension. And I'm going to assemble those together over the base B of the fibration. And the nice feature is this wants naturally to be an analytic space over whatever coefficient field we use to define our local systems. So I will explain this more precisely on the next slide. This is motivation for now, just explaining the general strategy. So this produces a first candidate space, and then we're supposed to remember that mirror symmetry cares about actually some quantum of corrected symplectic geometry. And in the world of Lagrangian submanifolds, in a symplectic manifold, that means not studying just their ordinary classical topology, but instead studying their geometry in the sense of Lagrangian Fleur homology or the Foucault category. So in first approximation, this analytic space, the uncorrected mirror, is what wants to be a moduli space of objects of the Foucault category of X, supported on the fibers of this Lagrangian fibration. And the classical geometry is what you would have in the absence of holomorphic disks. And when you have holomorphic disks, you need to modify the geometry of the moduli space of objects of the Fourier category to reflect the fact that the Floer cohomology is not exactly the same thing as the classical cohomology. So the corrections to the geometry of Numerov come from holomorphic disks bounded by the fibers inside X. And to organize them, it's useful to think of a key topological invariant called the Maslov index of a disk. The Maslov index of a holomorphic disk, well, it's basically like twice the first Chern class of the tangent bundle of X evaluated on that disk, except, well, that disk being something with a boundary, I need to say C1 relative to some boundary trivialization, given by the fact that we have a Lagrangian subbundle, so totally real subbundle of a tangent bundle at the boundary. Now, if you've never thought about this, that's kind of hard to digest. There's a much simpler recipe, given the setting we are in, which is that the first Chern class is represented already by this divisor D. And so the Maslov index is just twice the algebraic intersection number of your holomorphic disk with the divisor D that you deleted. Or didn't delete anymore, actually, not putting this in. So Maslov index governs basically how Floer theory interacts with the grading, cohomological grading in Lagrangian Floer complexes. And it also therefore dictates, if you want, in what degree of partial cohomology these deformations coming from holomorphic disks will live. So to stay closer to the Calabi-Yau setting, disks of Maslov index 0, the ones whose intersection number with D is trivial, for example, the ones that live entirely in this Calabi-Yau part of the manifold, their effect will be to deform the analytic structure of the mirror space. I will explain more about how that works in practice. And they also help us fix issues. These deformations also help us fix issues with the presence of singular fibers in our Lagrangian fibration. I will not say too much about it. In the Fano world, we care about disks now which do intersect the divisor D, and by positivity of intersection, the simplest thing that you might see is a holomorphic disk that hits D transversely once. These disks have Maslov index 2. They come in higher dimensional families. They are actually everywhere. And counting them suitably defines a function on the mirror, regular function, W, which is called usually the superpotential. And the role of that function will be to deform, to curve things on the mirror and pass from the geometry of just a space to that of what we call a Hirzebruch model, which has different meanings depending on what kind of geometry you want to do next. And so the new phenomenon that we'll get to at some point in this talk is that if you have negative Maslov index disks, the ones that hit D with a negative algebraic intersection number, then you get actually stranger deformations that break down the analytic structure of the mirror space and make it into something slightly more exotic. So you might ask, wait, but I thought D is a complex divisor. D is a holomorphic disk. Sorry, the disk is a holomorphic disk. They intersect positively, obviously. Yes, but when we count holomorphic disks, we have to deal with regularity issues. And so in practice, we also have to include things that might be stable holomorphic disks, namely configurations that are nodal, that consist of unions of disks and spheres. If you have a sphere component entirely something inside D with negative normal bundle, that can contribute negatively to the intersection. And so that's why in the title I say we want to look at non-Fano log Calabi-Yau pairs and see what happens. All right, so I'm going to go through that a bit more slowly and explain the construction. So there's some, actually, well, it looks fancy, it is fancy, but it's only classical geometry on this slide. If we have a Lagrangian fibration, then there is a natural affine structure on the base, which comes from measuring the amount of symplectic area between the Lagrangian fibers. One way you can do that is if you fix any loop little gamma on the fiber, just a homology class is enough, You move it from one fiber to another, it sweeps a cylinder. Symplectic area gives you a number, and you can do that for every class in H lower one of a fiber. This is a linear map, therefore you can associate, in fact, canonically, the difference of 2 points in the base close to each other with an element of H upper one of the fiber with real coefficients. So, okay, this was fancy and not needed. What I will do now is I will look at the space consisting of pairs of, so I'm saying a fiber of this vibration pi and a local system. So the local system, I think of it just as its holonomy. It's I think it as a trivial line bundle with a flat connection up to isomorphism. The important data is the holonomy. The holonomy is a homomorphism from pi1 of the fiber to the unitary group U1 over whatever coefficient field I use. I want unitary and one local systems. Okay, coefficient field, what's the field? So the field I want to use for symmetry reasons will be a Novikov field of formal power series in one variable t with real exponents. The coefficients little ai are in pretty much any field you want with say characteristic 0. I like complex numbers because that's simpler for life. This is done this way for convergence reasons. We don't know that quantities, counting holomorphic disks is hard enough to do like that. When you have infinitely many, you don't want to have to worry about whether the counts that you will produce converge. Morally speaking, so these exponents lambda I will be used to record the symplectic area. So the valuation of an element of a Novikov field is used to record the amount of symplectic area, people would say topological energy of the holomorphic disks inside. So when we have now a fiber of our Lagrangian fibration and a local system of the rest, we can combine the information from the position of the point B in the base of the fibration and the local system into a collection of local coordinates, which I will call Zi. If I choose a basis of the homology of the fiber, for each loop gamma I is my basis, I can define the coordinate Zi, local coordinate, by taking, so first of all, I record the amount of symplectic area between some reference fiber and the fiber I'm at. So T to the power of the symplectic area of the cylinder swept by that loop, times now a unitary element. Unitary in Novikov sense means valuation 0, means the leading term is a non-zero constant term, and then you have positive powers of T. So times the holonomy of the connection. So you get some non-zero element of the Novikov field whose valuation is equal to the symplectic area. So these local coordinates, they make your space of pairs look like a piece of K star to the n, a piece of some algebraic torus over, or analytic, rigid analytic torus, something over the Novikov field. But there's a projection to Rn by the valuation map, and this valuation projection coincides, agrees with the symplectic Lagrangian fibration projection over B. So in some sense, I have dualized my fibration, except each real Lagrangian torus is dual torus, is now a torus in the non-Archimedean sense for technical reasons. Okay. So the reason this is good for Lagrangian theory is that these coefficients, these weights that are T to the symplectic area times polynomial of the boundary loop, is exactly the accepted way to do weighting, to do weighted counts of holomorphic disks in Lagrangian Floer theory with Novikov coefficients and local systems. It's kind of a self-fulfilling prediction, maybe, but that's what we like to do for defining Fourier categories and for doing homological mirror symmetry. So a consequence of that is Lagrangian Floer theory of the torus fibers equipped with local systems lives, well, it works in families over the space X0, because you can redo the calculations for every possible object of Keeley Hoek that's there. And automatically, things will have analytic dependence on these coordinates of where you are in your modular space of objects. And so this is kind of the starting point. This observation was due first to Fukaya and then picked on by Mohamed Abu Zaid and then by Junwoo Tu and Han Yuan and others. This is the starting point of the family Floer theory approach to homological mirror symmetry. You build a mirror space in this way, and then you can use Floer theoretic constructions to transfer things from the Fukaya category of X to rigid analytic geometry on the mirror. So the way in which holomorphic disks mess up the geometry of this space of pairs and this coordinates with the I is governed by holomorphic disks. So if there's no holomorphic disks with boundary on any of your fibers, that's it, we're well done. This X check 0 is a modular space of objects of the Fukaya category with its natural analytic structure. If you are in a situation, say, like the toric-Fano variety, and if you keep deleting this divisor D, then the picture you have is actually correct in the sense that X minus D has no holomorphic disk, and you're done with building a mirror of X minus D. But then when you put back D in, this will deform the Fukaya category, and so on the mirror side, we need to deform the mirror. So this is, in a sense, what we're doing here. Okay, so the key concept here is this Floer theoretic obstruction identified by, studied by Fukaya or Ono, called M0. M0 is going to be an object, so an element of the Floer complex of the Lagrangian itself. And the role it will play is that it will be a curvature term for Floer theory. So in particular, the Floer differential doesn't necessarily square to 0, rather it squares to a commutator with M0. See the analogy for those of you who come from that world with matrix factorizations as a way of thinking of a curvature deformation of complexes of sheets. Okay. So what we do is we look at, this is just like slides for the symplectic geometers here, of which there's Kiyasha and Renato and a few others. Anyway, so we look at modular spaces of holomorphic disks in a symplectic manifold X with boundary and a given Lagrangian with one marked on the boundary. And we ask, okay, now there's an evaluation map from that to the Lagrangian. And what we do is the image of the evaluation map. So basically the locus of points which are on the boundary of a holomorphic disk defines some chain or co-chain or cycle annually or something of the Lagrangian. And for each class of disks, we will record this chain, or co-chain in our case, with a weight, which is this Floer theoretic weight, T to the symplectic area times polynomial of the boundary, which produces for us a generating function for these modular spaces of disks. So Maslov index here shows up in that the dimension of the space of disks in a given class is n minus 3, n is the real dimension of the torus, minus 3 plus the Maslov index. So points on the boundaries of disks is n minus 2 plus Maslov index. That means this locus is codimension 2 minus Maslov, which is why I'm saying here that I get a co-chain of the 2 minus Maslov index of beta. That's cohomological building. That's the codimension chain. So what we expect experimentally and from tropical geometry considerations is that Maslov index 0 disks, for example, the ones that live in the complement of the divisor D, will occur not at all for typical fibers of our Lagrangian fibration, and instead they will cluster along real codimension 1 loci in the base B, which we call the walls in this picture. So outside of these walls, the fiber is what we call weakly unobstructed, which means no holomorphic disks have Maslov index 0 or less. The next Maslov index is 2, the ones that intersect D just once. And the count of those well, will give me a cochain, actually a cycle with the minimal Maslov index of the V0, meaning actually a scalar multiple of identity. So that's the superpotential. And in more direct language, the superpotential is a weighted count. It's a generating series. We record with this weights Z beta, the weights of each disk. N beta is the number of disks in the class beta passing, whose boundary passes through a generic point of my Lagrangian. Okay. Yes. So the important fact is, in real life, of course, there's actually usually a countable infinite union of rules. So saying that a generic fiber does not bound disks is a little bit dicey, but we can still manage. Okay. So the simplest setting for testing all these things, and the most classical thing to do, is to look at toric varieties. And so toric Fano varieties were the first examples where one was able to compute this superpotential by enumerating holomorphic disks, find mirrors, and start verifying various things about homological mirror symmetry. So I want to look at the class of Hirzebruch surfaces. These are CP1 bundles of CP1, so rational old surfaces, obtained by projectivizing a rank 2 bundle of P1, which has splits at O plus O minus n, for example, where n equals 0, 1, 2, 3, and so on. So what that looks like, okay, there's a fan which is hiding behind talking. I think you can picture the missing vector in there. The moment polytope is there. Anyway, so this is a CP1 bundle over CP1. It has a bunch of fibers, which are just all regional curves. And it has two distinguished sections, one of which has normal bundle O of n, and the other one, the exceptional one, has normal bundle O of minus n. For n equals 0 or 1, this is Fano. Beyond that, not anymore because of the exceptional section. So, toric mirror symmetry, we just take the anticanonical divisor to be the union of the toric striker. What's left is C star squared. We look at product tori, and they bound no disks in the complement, so we are very happy that the mirror will look like a copy of the adjoint torus K star squared with this coordinates recording symplectic area between the fibers, so equivalent to the moment map. Okay, so one thing to know about, so the Hirzebruch surfaces topologically, you know, if you do first year with differential topology, you probably know there's only two kinds of S2 bundles over S2, the trivial one and the non-trivial one. And so the topology of this thing as a smooth manifold only depends on n mod 2. There's a complex deformation that deforms basically O plus O of minus n. You can deform it to say O of minus 1 plus O of minus n plus 1 and so on, and that lets you change n by 2 each. So you could imagine that F2 is just F0, which is P1 next P1, with a particularly special complex structure. For symplectic topologists, this is what this is. Of course, the divisor we're taking there is also very special because having this exceptional sphere in it is distinctive. Okay. So there is such a deformation, but the interesting thing is product tori in the Hirzebruch surface Fn can deform to Lagrangian tori in, say, F0 or F1, but not standard ones, actually what we call exotic Lagrangian tori, with more interesting enumerative geometry. Anyway, so we can calculate, you know, we can run the program from the previous slides. So starting with F0, which is P1 next P1, if I take a product torus, so the product of two circles in S2 times S2, you can work one factor at a time. In S2, take a circle. What does it bound? Well, you see two disks, one on each hemisphere. And you record that, and you have the two in the other direction. And remember, disks that only hit the bound of the divisor once in total actually have to be constant on one factor, and one of those two basic disks on the other factor. So there's basically, you know, disks contained in the vertical P1s and in the horizontal P1s. So now the weights of these disks, well, it's T to V are higher than some holonomy. we're going to give names to those coordinates. So I will declare that once I will equal Z1, the weight of the disk contained in the horizontal direction, disk times point, to one side of my circle. Then the disk on the other side, well, so the sum of their classes is the class of that P1. The total weight of that is T to the area of the P1. So the other one is T to the A over Z1. And then the other one, Z2, T to the B over Z2, where A and B are the symplectic areas of the two factors. And that is my Morse superposition. Okay, you can redo the same thing for F1, which is a blow-up of CP2. You find again 4 families of disks, one that heads basically towards each of the toric devices. And that's a general feature for toric fanos. The superpotential is always a Laurent polynomial with one term for each toric facet of your moment potato, whose exponent has to do with the corresponding ray of the fan. So the critical surface F2, which is what's sometimes called semi-Fano, because it still has, it's almost there, but it has just this exceptional sphere, the -2 section that has C1 equals 0, works almost the same, except as a first surprise. When we start counting carefully holomorphic disks, we see that there's an extra term that shows up on stable disks that are the union of that disk that's inside the fiber of the P1 bundle, connecting to the exceptional section. This nodal union of the disk and the sphere is actually regular as a nodal holomorphic curve. So if you deform the complex structure a bit, it will still be there, while things that involve multiple covers will not. And so we get this one extra term that counts these configurations. Okay. So next, things get even more exciting because we start having spheres of negative first chunk number, which means we start getting into less classical territory. And so this is ongoing work of my student Honghao Jing, who's over there, if you want to ask him questions about it. So you can study the critical surfaces, F3 and F4, where there's a bit of a surprise, I think if you haven't thought about it before, which is that even though in the toric world we expect no wall crossing because there's no disks in the complement of D, in fact, what it means to count stable disks becomes trickier because the answer depends on how you will choose a perturbation scheme to regularize your moduli spaces of disks. So if you pick a perturbation of a complex structure on F3, or an abstract perturbation scheme for regularizing moduli spaces of disks, for an structure, virtual fundamental class, whatever you want, you will have a slightly strange thing happen, which is best understood if you think of actual deformations of complex structure. So the -3 sphere in there is, of course, not regular at all. As soon as you deform, it disappears. But you might expect that its union with a fiber of the P1 bundle. So that is a nodal curve representing a class of square -1. You would hope that that will become the exceptional sphere in F1, the blow-up of P2 that you deformed. And that's true, but there can only be one. So in fact, there is one particular fiber which, together with the exceptional section, will deform, and the others will disappear. So the same is true for these disks that have already covered us in F2. If I take the disk that's inside the fiber that goes to the exceptional section, union the fiber, there's only one fiber for which this configuration survives the deformation as a stable nodal disk. And you can't, which deformation you choose determines for which fiber this happens. So now the enumerated geometry of the product torus depends on to which side of that fiber it lies. Which means we have actually our first instance of wall crossing in pure theory without even having had a singular fiber in our membrane fibration. That's a bit surprising, I think, to people who study this usually, because normally the source of wall crossing is the singular fibers that you see right away inside the fibration. That's the normal way this happens. And here what happens is we have a Maslov index 0 disk that's induced by the boundary. This configuration on the left produces a wall. Where that wall is depends on the choice of perturbation. So having done that, you can work out the superpotential for, you get two different formulas depending on whether your torus has a smaller or larger radius than the critical one of that configuration that deforms. So basically, that's the terms you would expect normally. The first green term that's always there comes from a double cover of that disk D union the exceptional section that does deform and counts with multiplicity 2. And the last term, which is different in the two cases, comes from basically a disk of Maslov index 4 that hits both the exceptional section and either the fiber over 0 or the fiber over infinity. But it hits the exceptional section exactly at the crucial value z that allows the smoothing when you take its union with the exceptional section. So basically, you can understand the geometry this way. And so the two formulas for the superpotential are related by a coordinate change. In this case, it's just a correction of the z1 coordinate by a correction factor, which involves, so t to the a over z2 is actually exactly the weight of this Maslov zero configuration that shows up on the rule. That's a general feature of how mirror symmetry works when you have these exceptional disks. And Honghao is also able to calculate the superpotential for the next Hirzebruch surface F4 in one of the geometric configurations that can come up. The expectation is that there are now several rules related to basically which unions of a double fiber and the exceptional section do deform to a curve of square 0. But anyway, so there's one chamber where you can calculate everything explicitly. And the remarkable new feature is that now there's infinitely many classes of Maslov index 2 disks that contribute to the superpotential. So this had been predicted a long time ago by Lagrangian and a few others, I think. But to my knowledge, this is the first explicit formula. And you can check that this expression has the same critical values as the usual superpotential of P1 times P1, but good luck finding the Wool crossing transformation that relates this to the usual superpotential of P1 times P1. Okay. Okay, so already in historic examples, we start seeing slightly exotic things caused by negative German number spheres, mostly like the usual argument that there are no disks of Maslov index 0 starts to fail, and that we start seeing Wool crossing where we shouldn't see it. And this is a good place for me to tell you what is Wool crossing. Then I will make it fail even more. Okay, questions about this, people? Okay, so Wool crossing, I've said the word before. What is it? It's the fact that despite what I told you about Floer theory varying analytically with where to put our Lagrangian torus and so on, actually there are discontinuities. And discontinuities are caused by bubbling of holomorphic disks. So unlike moduli spaces in Gromov-Witten theory, which are always pseudo-cycles, meaning bubbling is real to dimension 2, so that doesn't matter for counting. There's always fundamental classes of moduli spaces and so on. In Lagrangian Floer theory, the moduli spaces do have a boundary. The boundary of the moduli space of disks is a moduli space of pairs of disks attached to each other at the boundary point. And so that means if you're counting Maslov index 2 disks, which you expect exist in the high dimensional families, that you can make a count of how many of those exist through a typical point of your typical Lagrangian, you may have discontinuities when one of those disks decides to break into a union of two smaller disks. Maslov index is additive under the unions. So the way that 2 might decompose is 2 plus 0. If you hit a wall of Maslov index 0 disks, typically Maslov 2 disk can break, and then the big disk you have no longer exists. Or seeing the picture in reverse, you have a kind of holomorphic disk you like. It can actually, well, it will survive passing through the wall, maybe, but maybe new disks will appear out of attaching the exceptional disk to it and then smoothing. And the point is that nodal configuration in the middle can be smoothed, but only to one side of the wall or the other. So there's a jump in the counts of disks. So what's remarkable is normally when you say a function is discontinuous, you worry about how its values change. And here you shouldn't do that. Instead, the structure of the discontinuity that was first, I think, observed by Fukaya and Otamono is that there is actually a coordinate change on the domain that corrects the discontinuity. And so these are wall crossing coordinate changes, where basically the coordinate that gives the weight of that disk, z beta, gets multiplied by some function involving the variable z alpha, the weight of the exceptional disk, that you can think of as some generating series for Maslov index 0 disks at the wall, except you have to worry about also multiple covers of them and disjoint unions of multiple covers, and somehow this all goes into this transformation. So the slogan is that the corrected mirror should be built by gluing together the local pieces of uncorrected mirror under these wall crossing transformations. And the point is, this becomes, what would say, a modularized space of actual objects of the Keeley category, which are our Lagrangian tori, together with bounding cochains or other information that helps us correct them to avoid these bad Maslov 0 or less disks. And so this is, in symplectic language, also the heart of the Gross-Weber program for building mirrors by drawing scattering diagrams and computing wall crossing functions and building mirrors out of that. And the axiom that really helps with this to work is that wall crossing transformations are consistent. They satisfy a co-cycle condition when you go around the loop in the base. And this tells you that the mirror is going to be a well-defined analytic space. The proof of this consistency, this co-cycle property, relies on a very important fact that the interactions between different types of walls are about what happens when you see several kinds of Maslov index 0 disks. So here I've been telling you about the boundaries of modular spaces of Maslov 2 disks being Maslov 2 plus Maslov 0, therefore Maslov 0 governs the jumps. But it's also true that the boundaries of the spaces of Maslov 0 disks are pairs of smaller disks themselves. And so if Maslov 0 disks only break into pairs of Maslov 0 disks, this is how you get to what it ultimately becomes the consistency condition. And so the problem is if there are negative Maslov disks, then a Maslov 0 disk can also break into positive plus negative Maslov index. And that causes the consistency of scattering diagrams to fail. Okay. So that seemed at first scary but hypothetical. But unfortunately, it does happen in examples. Now, the good news for people who study Calabi-Yau, this doesn't happen in Calabi-Yau because Maslov index is always 0 in Calabi-Yau. It's after all the algebraic intersection number with the divisor D. If this divisor D is empty, as it is in Calabi-Yau, you don't have to worry. Like, this is only a problem for log Calabi-Yau pairs where D contains negative rational residuals. Anyway, so the example is a bit technical, so I'm not going to read to you everything that it says there. But if you want to engineer an example where this shows up, what you do is you start from a toric example, and you modify it by blow-ups to produce a nice, easy to study rational curve with a sufficiently negative normal bundle that will interface with some holomorphic disks to produce regular stable disks with negative Maslov index. And then you can study how this comes together. So one way to do that is you start with a total space of O of minus 2 over P1. That's actually most of the Hirzebruch stuff is F2. That contains the 0 section, which is a rational curve with normal bundle O of minus 2. Take the product with C squared, to have more space available to you. So now you have these spheres with normal bundle O plus O plus O of minus 2 that has C1 equals 0. That's okay, not too bad. And now we're going to do a blow up, which is a pair of blow ups. So what we do is we'll blow up at C times 1 times the fiber over 0, and at 1 times C times the fiber over infinity. What's the goal of that? The goal of that is that my spheres that have normal bundles O plus O plus O of minus 2, that existed for every point of C squared. Now I'm doing so that if, in fact, my first coordinate in C squared was equal to 1, then one of the O's in the normal bundle becomes an O of minus 1, because I passed through the locus of a blow-up and the proper transform has picked up a bit more negativity in its normal bundle. And then the sphere over 1, 1, same thing if the second coordinate is 1. So the sphere over 1, 1, no, the point 1, 1 times the 0 section becomes a sphere of normal bundle O of minus 1 plus O of minus 1 plus O of minus 2, which is regular inside this 4 manifold, but there, sorry, fourfold, but there. And so now I can study product Lagrangian tori, or rather lifts to the blow-up, which show up in doing SYZ mirror symmetry for this blow-up. It helps that before this, I spent about a decade of my life thinking about SYZ mirror symmetry and blow-ups toric varieties. And so you can actually calculate things, because basically you can start from the toric variety, where you can calculate the superpotential because it's just, you know, the disks that you see along the various coordinate factors, as in the toric case. And now you just modify things in the blow-up, but because you observe that, well, if you have also more complicated disks which have higher Maslov index in your toric variety, but that pass through the locus that you blew up, then they become lower Maslov index disks in the blow-up that will contribute to your counts. So basically, we need to count, you know, disks in the toric variety which pass in a certain way through the loci that I blew up. You know, so you can do a lot of calculations. It's a huge mess. But what you find is that the geometry depends on whether your product torus in the C squared factor has radius less or more than 1, because that will determine whether the holomorphic disks in bounds in C squared do or do not intersect the blown up loci, which are at, you know, coordinates equal to 1. And if the radius is bigger than 1, then you have extra contributions from things that do something interesting exactly as that coordinate that is 1. And so you can do all the calculations. And then what you find is that, in fact, the coordinate changes that give the wall crossing are not going to satisfy the post-cycle condition. You have an inconsistency in the wall crossing diagram. And the cause of this is that when you take a product torus in C squared of radius 1 and 1, at the point 1, 1, you can place a disk there that heads towards the 0 section of your O of minus 2 over P1, and attaches there to this very exceptional sphere with normal bundle O of minus 1 plus O of minus 1 plus O of minus 2. And this thing is a regular stable disk of Maslov index -2. And the Maslov index 0 disks breaking into that plus Maslov 2 disks causes inconsistency. So at that point, you know, you have two options. One is declare, well, who really cares about these things that are not even semi-Fano or anything? That's maybe the same thing to do. Or the other thing you can do is say, hey, this is cool, a new geometry. I have no idea what this is. Let's play with it. Yes?
So usually we see the fifth line, the fifth ray in your wall crossing. So is that something is missing here? Or?
No. Oh, there's no overlay because these wall crossings commute. You see the.
You said that they did not.
No. Oh, sorry. So what's happening at the intersection? So if you compare like the phi0 minus and phi0 plus, they're almost the same. They're walls that just propagate like along the affect the Z1 variable. There's just like this extra term in orange in the top right corner that's there. That term comes from having picked up a Maslov -2 disk in the middle. It doesn't come from interaction with the other Maslov 2 disks. The example is engineered so that actually there's no classical scattering between the two families of Maslov 0 disks. Essentially because they run parallel to each other and they don't talk to each other in any useful way. So I didn't want to deal with usual scattering on top of the rest. So all that happens here is in this place where the walls meet, there's also this additional Maslov -2 disk that causes the wall functions to be modified. But they're modified basically not by commutator with the other wall crossing function. That commutator is trivial. It's rather by picking up this little extra term from the Maslov -2 disk. My guess is one could try to build, I don't know if one could try to build an example that doesn't have Morse crossing there, so that we can study it more in isolation. I don't know how to do that. That's impossible. So, question you might ask, so let me go back to this. Sorry, so the thing to note though is there are these 4 charts which look like pieces of K star to the 4 with 4 coordinates Z1, Z2, Z3, Z4 with these regular functions, superpotentials, and pairwise they're glued to each other by these analytic coordinate changes, and the superpotential glues nicely, and everything is just fine except for the consistency condition in the middle. So what that means also, so these various coefficients Q, Q prime, and so on, they are like weights associated to various kind of rational curves inside this. So you see that all the nasty terms, I try to isolate them in orange. The orange terms all have this Q prime, Q double prime in them. That's the weight of that very special exceptional sphere that's there, that's causing our troubles. So first thing you might do is set Q prime, Q double prime equal to 0. And then what you get is a completely fine Lagrangian models. Then you can ask, what is the deformation induced by these orange terms? How do I understand that once I turn back on the Maslov -2 disk and the other things that follow from its existence? So one way to think about that is, well, deformation comes from Herschel cohomology, if you believe in category as a first principle. In homological norm symmetry, we believe that categories exist before the spaces, and that we just look for spaces that reflect the geometry of categories, maybe. So you might say, okay, I want to study the Herschel cohomology of the B-model categories, matrix factorizations of this Lagrangian model. There's a result, I think it's Lin and Goberleano, and maybe some others too, that says that this is actually the hypercohomology of Pauling vector fields on this narrow space, deformed by interior product with the derivative of the superpotential. And so the Maslov -2 disk determines a class, a deformation class in there, which we can actually see explicitly from the geometry of the wall crossing. So the leading term is in a place that's a bit exotic, and that's why we're leaving classical geometry. It's a 2 co-cycle with coefficients in wedge 2 of the tangent bundle. So check 2 co-cycle, that's convenient if our goal is to understand inconsistency of gluing of transition functions. Check 2 co-cycles are the right place for that. Wedge 2 of the tangent, that's because basically, well, this is the geometry that's there. So this co-cycle, actually, you can take it, I don't really want to explain how bilectron is set up just yet. That will come later in the talk, which might not make it into the hour. But the coefficient in front, Q prime, Q double prime, Z4, that's exactly the weight of that stable Maslov -2 disk. So on the other lap of coordinate charts, you see this coefficient coming up as a bilector field. Well, actually, probably that has to do with Poisson stuff and so on. Anyway, but to complete it to a co-cycle in the Herschel complex of this thing, you need to add some terms also in lower degrees, because the differential has been deformed. This is not closed for D plus interior product with dW. And those other terms are the corrections induced by that Maslov minus 2 disk on the wall crossing functions and on the superpotentials. So in some sense, the outcome is what I would like to call a deformed Landau-Hirzebruch model. It's locally a space with locally an analytic function W. But the coordinate charts are glued very nicely, but in a way that's not satisfying the co-cycle condition. And the way the co-cycle condition fails is by the interior product of D of the superpotential into this two co-cycle, two co-something. And you see now that when you interior product with dW, you get check two co-chain with coefficients in the tangent, which is where inconsistency of gluing overlaps of analytic structures should live. Okay. So to make sense of this, what we like to do is build, in fact, the geometric structure on the uncorrected mirror that will record these corrections, regardless of whether it's the usual superpotential as a function, or the Maslov zero disks, which will give us correction of the analytic structure, or these further weird things. So one thing you can do is you can do Lagrangian field theory, not just for a single Lagrangian fiber at a time, but letting, consider the whole family of Lagrangian fibers. And then these weights Z beta that used to be numbers, T to the area times the holomorphic of the particular connection, they become actually variables in this family sense. So we'll do Floer theory for a family of Lagrangian fibers with coefficients in some completion of the Laurent polynomials with Novikov coefficients in n variables. So these coefficients, they are where these weights Z beta live, and I want to complete them to allow for the kinds of series that I get in Floer theory. So I want actually all Laurent series which Novikov converge over a given range of valuations. This forms a sheaf over the base of the fibration, and it's basically corresponding to the sheaf of rigid analytic functions on the uncorrected mirrors. That's why I'm calling it ON. It's like the push forward of the sheaf of functions on the uncorrected mirror under the evaluation projection. So you can do Lagrangian Floer theory counting this with boundary on any fiber about a fixed fiber of the fibration with these universal coefficients. And this again has curve for infinity operations. And this has a curvature term M0, which now will be a cocycle on the base V0 with coefficients in co-chains of the fiber with coefficients in this O1. Again of degree 2 minus Maslov index. So the expectation is, on one hand, from tropical geometry, we expect that this various Maslov index occur along walls, or I don't know what you would call a wall of higher than pillars, I don't know, slabs, no, I don't know the name. Anyway, codimension I walls, and codimension I in the fiber of those walls would be where this of Maslov index 2 minus 2 times I would occur. So this M0 should have a decomposition into part that counts Maslov 2 disks is in fact going to be degree 0 lives everywhere. The Maslov 0 disks live in codimension 1 in the base, codimension 1 in the fibers over those, and so on. And tropical geometers will not list all this. And the next expectation is that M0 satisfies something called the master equation, which is that it's classical boundary, especially as a check co-chain on the base, plus 1/2 of some kind of bracket of M0 with itself vanishes. And this part is kind of a bit slurpy. There's probably actually an L infinity deformation of this equation going on. So I need to tell you a bit about what this master equation is and what it does for mirror geometry. So counts of holomorphic disks where we record their weights by these variables z beta that are the universal weight of the disk in the class beta. And they also have, of course, they trace out certain things inside the fiber, which I believe should be closed. So that's why I put HI of the fiber. And then they label certain things in the base. So that's why I put codimension I co-chains. So this decomposition of M0, so these terms. Okay, so first, what is this bracket I was telling you about? So the bracket is really weird if you see it this way. If we have a term in there, which is so z to the gamma, it's like one of those weights that reminds me that what I'm dragging with me came from disks whose boundary, total boundary loop, was actually representing the homology class gamma. Times alpha is a cohomology class on my torus, telling me where inside the fiber those things live. So observe, we have the cohomology of the torus, tensored by the grouping of the first homology, that's a funny operation you can do, which contracts the H lower one class into the cohomology class. And then you skew symmetrize. So basically you multiply the coefficient z to gamma, and you wedge the, you do the curve product in cohomology. The first thing to do is you do an interior product of the weight of one of them into the cohomology class of the other, or vice versa. So this is a degree -1 bracket. And the mystery is maybe less if you realize that this weird thing, this cohomology with weird coefficients, is in fact the homology of the free loop space of the torus. And what I wrote for you is the transcription of the Chess-Sullivan string bracket on the loop space. So now the fact that holomorphic disks want to break into pairs of holomorphic disks should tell you that M0 should indeed satisfy some equation that involves the string bracket. That's basically the intuition for this master equation. So now under mirror symmetry, things get really beautiful because H upper one of the fiber is the same as the tangent space to the base of my Lagrangian fibration. That's the fact that the amount of area between two Lagrangian fibers defines a one co-cycle. It's class an H upper one. And so that means the cohomology of the fiber with completions of the grouping of H lower one coefficients becomes isomorphic to the push forward under the mirror valuation projection of polyvector fields. How? Well, the weight z to the gamma was already an analytic function on the mirror, so the function becomes the function, that's fine. And now the cohomology classes, well, the basis of H upper one can be identified as the basis of vector fields in what I will call the log zi coordinates. And so you just take wedge products to wedge products and you get polyvector fields. So under this transcription, M0, which counts boundaries of holomorphic disks, becomes some sum of terms under that assumption, which are each I co-chains on the uncorrected mirror with coefficients in I polyvector fields. And the funny bracket over there is the Skelton-House bracket on polyvector fields, enriched by the curve product of cohomology. Okay, so and the master equation then becomes some kind of Mark-Cartan or whatever master equation as well, I guess. And so we finish here, I think. The master equation amounts to the claim that if I take the usual differential on cohomology of polyvector fields, but I deform it by adding the bracket with this W, this forms now a new differential squares to 0. So if you write this term by terms, it says expanding W into its various derivative components. The first equation you see is that, I mean, this involves a lot delta plus the bracket with W1, the part which is a 1 in C1 with coefficients in the tangent, which is the deformation of analytic structure, says that W0, the part which will become the superpotential function, is closed under that. The next thing says this delta plus W1 squared is not 0 anymore, but rather is the bracket with interior product of W0 and W2. That's the issue we identified on our example. And then there's further things. So the philosophy here is you should see this delta plus bracket with W1 as a deformation of analytic structure that people talk about when they say, oh, wall crossing transformations and this and that. Concretely, if you use a check model, you didn't say what kind of cochains I was using. If you think check, this is deforming the bluings between the coordinate charts. If you think of it in the Dolbeault world, you could try to make this deform a delta operator by W1 now becomes a 0-1 form with values in the tangent. And then the first equation says W0, the superpotential, is analytic with respect to the deformed structure. And the second equation says the deformed structure is actually not quite an analytic space by this amount. And now you can ask, what is the meaning of this thing? So in the check world, it's about failure of co-cycle conditions for Boolean charts. What's more fun, I don't know what to make of it, but the Dolbeault world, well, this is exactly the kind of thing, 0-2 form using the tangent. That's the Nierenhaus tensor of the deformed delta as an almost complex structure. So even if you're stuck in this world, a piece of good news is that the critical locus of the superpotential, which is the part that everybody cares about, along that, this term vanishes because interior product of dW0. And so the consequence of that is the critical locus of the superpotential on one of those weird deformed Hirzebruch models is still an honest analytic space. You can still do whatever you like to do with it. But the space around has gotten a bit weirder. Okay, I think this is a good place to stop. Thank you.